Good afternoon here. So it will be presented by Dr. Mahidar Satineni, and Mahidar received his MS and PhD in aerospace engineering from UCLA. He currently leads the user services group at SDSC. He has led the deployment and support of SPC and data application software on several of the NSF and UC resources, including Comet and Gordon at SDSC. Today in the morning keynote talk, Professor Mike Norman indicated about these machines. He has worked also many NSF-funded optimization and parallelization research projects, such as petascale computing for magnetosphere simulations, MPI performance tuning frameworks, hybrid programming models, topology-aware communication scheduling, big data middleware, and application performance evaluation using next-generation communication mechanisms for emerging SPC systems. He's a co-PI on the SDSC Comet and also on the Expanse SPC system projects at SDSC. Professor Mike Norman also introduced this Expanse system today morning. So Mahidar will be talking about application and microbenchmark performance study using MVAPICH2 and MVAPICH2-GDR on SDSC Comet and Expanse. So let's welcome Mahidar. Please share your screen and you can get started.
Thanks, DK. Let me get started with the share screen. That looks good, right?
Looks good. Yes.
Okay, great. So yeah, as Dr. Panda indicated, I'll talk about some of the initial benchmark results that we've got on Expanse hardware. I was hoping I could do a lot more today, but we are still kind of installing the system. So I'm going to give you some preliminary results, but it should be a nice intro to the performance on the AMD hardware. So the talk itself, in terms of how it's structured, I'll just go quickly over the IB-based clusters that we've had at SDSC, and we've used MVAPICH all the way through the past few systems. I'll also quickly go over a Comet hardware summary, just so you know how we started from there and evolved to the Expanse structure right now. And then a bit more detail on the Expanse hardware. And then I'm going to talk briefly about the application and software library stack on SDSC systems. We are kind of moving from using ROX on the previous systems to using a SPAC-based. So we started using MVAPICH with the Trestle system going back to 2011. That was a AMD-based system, Magny-Cores processor. I think it was 32 cores per node. And QDR InfiniBand and a fat tree topology, and we had MVAPICH2 on that. Then we went on to Gordon, which basically was the first dual rail QDR system, I think. And so we did use MVAPICH2 with the 3D Torus support on that system. And the current system that's in production and will be there till 2021 is Comet. That came up in 2015. That featured basically Intel Haswell processors, an FDR InfiniBand with a fat tree topology. There was oversubscribed 4:1 between racks. We also, as Mike indicated in the first talk, we did virtual clusters on the machine. So there was a lot of different MVAPICH flavors that we tried out on there. MVAPICH2, MVAPICH2X, MVAPICH2-GDR on the GPU nodes. We also did the SRIOV based MVAPICH2 also. And then the upcoming system Expanse, which should be in production in October, is essentially 728 nodes of AMD EPYC 7742. It's the ROM processor with HDR100 on the nodes. And I'll go into a little bit more detail in the architecture piece. It's also a fat tree topology with 3:1 oversubscription. So Comet itself, just this is kind of the baseline for all our performance comparisons. So that's the reason I'm kind of showing you what we had. So it's 1944 standard compute nodes, with 128 gigs of RAM and 2.1 gigahertz DRAM. And then, so going from here to an expanse node, we're going to have 128 cores. So it's a huge step up in the number of cores. It also has extra memory channels and faster memory, so it kind of evens out in terms of per core performance. And on the 72 GPU nodes of Comet, we initially had 36 nodes with K80 cards, and then we added 36 more nodes with P100s. And as I mentioned, it was a 4:1 oversubscription on Comet. Let me just move that a little bit. Okay. In terms of the performance storage, we had a Lustre-based file system, actually two file systems that aggregate to 200 gigabytes per second. So in terms of Expanse itself, it's a capacity system, category 1 under the NSF award number there. Mike Norman's the PI, and then all the co-PIs, Ilkay, Amit, me, and Sean are listed there. We've run some preliminary benchmarks, not on the Expanse hardware itself, but on some of the Dell clusters and test clusters and other test resources we have access to. And we see that on a per core basis, we see anywhere between 1 to 1.8x performance improvement. And this really depends on the code. Like if you're really memory bandwidth bound, you might see something closer to the 1x, that is equal core per core. For others, you can go all the way up to 1.8x improvement in terms of on a per core basis for the applications. Now, Expanse has almost 2x the core count of Comet. So that leads us to basically believe that we can easily go more than 2x throughput over Comet. And we've been testing and building a lot of the software packages already on the test cluster, and we've essentially built the Comet stack on the Expanse test cluster, and the performance looks reasonable as expected. We are obviously still tweaking a lot of the MPI implementations, and hopefully with a lot of support from Dr. Panda's group, we should be able to improve things even more, I think. Overall, since it's x86 based and since we have most of the stack from Comet built on the Expanse system, we expect a pretty smooth transition for it on a user level. That's the brief overview of the system. Basically, it's built from 13 scalable units. So actually, maybe I can go back to the picture in the front and show you the scalable unit. So that you can kind of see one of the scalable units here. So you have all the GPU nodes on the top, and then the compute nodes below that. So each of the scalable units has 52, let me get that right. 56 compute nodes and basically 4 GPU nodes, I think, on each of the scalable units. And all of this plugs into a 40-port 200 gig HDR switch. And we do the splitting of the 200 gig into two HDR 100s, and that's how we get the 80 ports and with the 60 nodes. So you get 20 uplinks. So you get a 3:1 oversubscription between racks. That's the math behind the network. In terms of data, we have node local NVMe based storage. It's a 1 terabyte on each compute node and 1.6 terabytes on each GPU node. And we'll have 12 petabytes of performance storage from Aeon. That's going to be 140 gigabytes per second. And with flash in the NVMe in the MDSs, you can actually push the IOPS up quite a bit. So should do reasonably well on the IOPS in terms of scaling out. And then we will also have a 7 petabyte Ceph object store, which will kind of be the place for all the projects storage during their allocations, and also kind of serve as a staging point for data that you either use in the cloud or in a Compose system. So that's the gory details of the each node. So basically, it's a 2.25 gigahertz processor, 64 cores on each socket, on each processor, 2 sockets, so you get to 128 cores, 256 gigs of RAM. So this is a little less, actually, less memory per core than Comet, but based on what we've seen of memory usage on our typical application, we should be good with that, I think. On the GPU nodes, we have basically V100 GPUs with 32 gigs of memory each with NVLink connectivity. So I wanted to briefly go into the processor architecture design because it is relevant on the application side, and I'll show you some extreme examples kind of to illustrate what happens with the layout. So it's an AMD EPYC 7742 processor. Essentially has 8 core complex dies, so those green boxes there. And there's a central I/O die, which is a 14 nanometer technology. So with this hybrid setup where the 7 nanometer processors and the I/O at 14 nanometer, you can essentially pack in and scale out very well. So you have 8 memory channels per socket. And there are different ways you can segment them into NUMA domains, and that's another thing I'll go into. The DDR memory is at 3.2 gigahertz. And these memory and I/O can be abstracted into quadrants with 2 DIMM channels and 32 I/O lanes. So each of those green boxes there, the core complex dies, has 2 core complexes with 4s and 2 cores in each CCX, and they share a 16 meg L3 cache, and a total cache is 256 meg. And each core contains a private 512 kilobyte L2 cache. So how do you break this up in terms of the NUMA domains? So the 4 logical quadrants you can partition into different NUMA domains, and the option has to be set in BIOS. And these domains are essentially designated as NUMA per socket. On the HPC configuration, we're going to do NPS 4, which is 4 NUMA domains per socket. So the various configurations basically that are possible, and this is all from the AMD developer guide. So the NPS 1, the processor is a single NUMA domain. So the memory is interleaved across all 8 memory channels. This is really useful if you have a workload that's not NUMA, where the NPS 2, you're partitioned into 2 NUMA domains, and half the cores and half the memory on one domain and the other half on the other. And the memory is interleaved across 4 memory channels. So the one that we typically going to use on an HPC system, because typically our workloads are NUMA aware, and ranks and memory can be pinned appropriately, so you have some control of what you're doing. So it's efficient to do this kind of configuration, where each quadrant is basically a NUMA domain. So in each NUMA domain, you have 2 CCDs, so that's 16 cores and 2 memory channels and 32 PCI lanes. The PCI devices will be local to one of the 4 NUMA domains. So that's the thing to keep in mind. And then this is kind of what we'll be using. So that was the CPU node architecture. On the GPU nodes, we basically have 4 V100s, 384 gigs of RAM, so that's a lot more memory than we used to have. And these nodes actually have Intel Cascade Lake processors, and they have 40 cores per node, I think. And this is the topology of it. So you have NVLink between all the GPUs, and it's split between the two sockets, GPU 0 and 1 on the one socket, and GPU 2 and 3 on the other. And this has the weird odd even numbering that you see on Comet 2. So that kind of was the hardware. In terms of software, I think we saw this slide in the morning too. Basically, Comet's been supporting a really broad user base, large application and software library stack, and thousands of users. So Expanse is really an evolution of this. So we expect to be doing the same kind of broad user base and application stack. Just to get a sense of how the application stack looks on Comet, this is not the full list, but you can kind of see we have all kinds of domains: biochemistry, bioinformatics, machine learning, quantum chemistry, structural mechanics, viz, molecular dynamics, and so on. And then a bunch of math libraries that, you know, like as an aerospace engineer, I might be using a lot of these. So it's a pretty diverse stack. And on the current setup, what we typically do is everything is managed via modules from a user's perspective, but on our side, we are packaging these into ROX roles that are deployed on our systems. This was a nice thing when Comet was coming up, because we essentially benefited from the work we did for all the previous clusters, and these ROX roles are just rebuildable across the new environments. For Expanse, there's a few changes. The system deployment and the system, the cluster management is going to be done with Bright. And then on the application side, we are moving to a stack-based approach. And the motivation was essentially the software stack is getting really diverse, and it's difficult for like one group to support the entire breadth of the software stack with so many different new applications coming up. With SPAC, we can leverage the work of a wider SPAC community for some of the installs, so that helps a lot. And also we have a mix of architectures and the ability to have multiple installs, customizing and optimizing for specific targets kind of gets really easy with SPAC, so that's kind of why we went the SPAC route. And also, like if you're having systems like Expanse that essentially feature cloud integration and composable systems as an option, you want to be able to replicate the stack pretty easily, and this can help also. Now, on the AMD ROM side, there's some compile and runtime considerations. Obviously, this is like a very high level thing. We probably will have workshops down the road which go into a lot more detail. But in terms of what we have tested with AOCC compilers, GNU and Intel, and we've seen a mix of things with different applications doing better with different compilers. So we will be kind of using the right combination for the applications that we find the best performing, essentially. The MPI versions, we've tried out MVAPICH2, OpenMPI, and Intel MPI. And as you saw, that the processor architecture is quite different from the current simple two-socket thing. So with the various NUMA domains, and so I think it'll be really critical to have the right binding options and affinity flags. And we will be developing scripts so that users can do this easily. And I'll show you one of the examples today. And then the other thing I wanted to talk about was Singularity on the SDSC system. It's been available on Comet since 2016, and a lot of the machine learning type codes essentially come through that, mainly because it's hard to keep up with the OS requirements that keep changing rapidly. So it's been an easy thing to go via Singularity image. And then we have a lot of people who have commercial applications where they have binaries with specific OS requirements, and they don't mention the I mean, they don't have options to change that. They don't have the source. So Singularity helps in such cases too. And we've done other things like in training, we've encapsulated all the requirements in an image, so that makes it easy for people to try it out, both on Comet and outside of Comet. And we've actually tried MVAPICH2-GDR through Singularity Controllers. I left these slides and I've talked about this before, so you can take a look at what exactly we did. But basically, you can match the driver and the OFED stack, and then use MVAPICH2-GDR inside a container. And if you wrap the MPI run RSH scripts the right way, the SSH gets wrapped the right way, you should be able to actually launch it within the container. Now, in terms of applications and microbenchmarks, so we do this with pretty much all the new systems. We run a ton of microbenchmarks like OSU benchmark, IOR, Stream, FIO, DGEM. And then we also have a suite of applications that are quite commonly used. So like on our systems like GROMACS, NAMD, Neuron, OpenFOAM is a fluid dynamics code, Quantum Espresso, RAxML is a phylogenetics code, and WRF, which is a weather code. And similarly on the GPU side, we see a lot of Amber, NAMD, Beast, and a lot of the machine learning usage. So these are the kind of benchmarks we run. The preliminary results for some of these things from the development system are what I'm going to show today. And in some cases, I didn't get a chance to run them yet, so I'm showing you some prior results from Comet. So just a quick thing showing on Comet from with using MVAPICH2-GDR using containerized approach. This is an old test that I did. You can see that native and container, there's practically no difference in terms of the latencies. And then a TensorFlow benchmark, again running via Singularity. Oops, okay. And you can see on the P100 nodes, if I just pick the GPUs that are on the network side, you get pretty good parallel efficiency and scaling out to several nodes. I think this was a 5-node test. And I've actually tested this with V100s on a different system that's hosted at SDSC. It's a Simon's Foundation one, and I used MVAPICH2-GDR again via the containers with 4 GPU nodes, 4 GPUs per node with the Intel Skylake. So the Expanse node has 4 NVIDIA V100s with Cascade Lakes, so I expect them to show very similar performance. And you can see that it scales out pretty well, going out to 8 GPUs. And on Expanse, we'll probably run a much bigger test to see how this scales. So the initial benchmarks on the AMD ROM hardware, I think I went through the list already, so I should just switch to the thing. So one quick note on the Expanse dev system, it was actually a single socket AMD EPYC processor per node. So 64 cores per node, HDR100 and the HDR200 switch with the split cables like we have on the production Expanse. So you should expect something similar on the production side. So the first benchmark is a RAxML benchmark. It's a phylogenetics code which does MPI plus P threads. Now, I had to be really careful with this one because you can pin MPI tasks pretty easily, but the threads will move around if you don't set them up right. So one of the things I did was write a wrapper script that essentially uses task set under the in the wrapper to kind of pin the P threads to the right cores. And just so that I was sure that I was doing the right thing, I looked at HTOP from a 20 core run on the left and a 40 core run on the right, and you can see I did a very compact 1 to 20 core binding. So that's basically what, if you think back to the picture I showed you with the NUMA domains, This means that I'm actually not using all the memory channels because I'm kind of keeping it compact to the first two NUMA domains. And this was deliberate because that's the real scenario, right? The node's not going to sit idle with letting you bind to all the cores. So when I'm doing a 20 core run, I want to be sure that it's actually realistic. And in the next page, I'll show you like the impact can be quite drastic if the code is memory bound. So in this case, you can see the comparison between Comet. We ran it on Stampede 2, and which has the Skylakes, and then the Expanse Dev, which has the AMD ROM. And you can see for this code, we're doing pretty good, going out to 40 cores. So the next thing we tried is a Neuron benchmark, and this actually is dominated by communication. And since on node you're going to essentially do shared memory, it gets essentially bound by the memory bandwidth. And so I did two sets of runs. One was the compact case where I basically make sure that I use the minimum number of NUMA domains. So for example, with the 16 cores, I can just pick one quadrant and have two memory channels. And then with the 32, you'll have 4, and with 64, you'll have all 8. So you can see it scales well, like it's completely memory bound. So you kind of see that scaling there. But you can cheat and go back and put like the 16 cores across all 8 of them memory channels. And you're leaving a lot of cores idle if you do this, of course, in production. So you can't really do this, but just as an illustration. So you can see that there's a pretty big difference in the performance. And again, this is an extreme case. I just wanted to show you that it will matter actually on how we bind things and how we do things. In terms of scaling, I just wanted to show you some that go beyond single nodes so that you can see the network performance also. So this was on a Dell cluster with EDR IB, which will be the same as 100 gig HDR 100, so it should be good as a comparison. And you can see when the core count is all on one node, you can kind of see there's not much difference between Comet and the ROM platform. And actually, you'll see that even with the Stampede 2 in this case, because it's really memory bound. And then if you scale out, you can see that we're doing fine going out to 768 cores. Now for Comet, it gets a little worse as you scale out because the number of nodes is increasing, and then the collective gets hits more and more network links essentially. On a different code, basically a quantum Espresso benchmark, you can again see that we're doing better than Comet in terms of per core performance, right? And this is again going out to, I think this was 3 nodes on Expanse and 6 nodes on, or a lot more nodes on Comet. And then on the GPU side, I didn't get a chance to test the MVAPICH2-GDR yet on the test cluster yet, but I did try out like a threads-based code beast, and we're doing pretty much as expected on the V100s in terms of performance. This code is not completely GPU bound, so you don't see as much of an improvement as you would say see with NAMD or sorry, with Amber or some other codes. So that was a quick look at what's been happening on Expanse. If it was a week later, I probably would have a lot more scaling results, but we will keep putting those out as we progress and get more testing done. In terms of what's happening with Expanse, actually on the allocation side, the first extract submission got done in July, and the review is going to be held next Monday, and the allocations start in October. There was a question. Sorry, I just saw the question on the Lustre version. I'm pretty. I'll have to check on the version. You know what? I'll put the version in the not in the chat, but probably
in
on
the
the
Slack, yes.
Slack channel. Yes.
Yes, yes. That will be helpful.
Yeah. Because that's a question beyond my. But I know it's an open source version, so like nothing that. Anyway, we can look into that. And in terms of the upcoming XRAC submission period, there's one that's coming up in September, and that will be for allocations that start in Jan. We will also have an early access period. I think Mike mentioned this. I'll actually be sending out a news post very soon, probably in the next couple of days or early next week, depending on how things play out, but it should be soon. And you can apply, and basically, obviously, it's going to be a test period, so we'll have to work with you in getting things sorted out if needed and so on. But we'll be happy to have people on soon. Right now, what's going on is the OS is getting installed and the early system testing is going on. And once we have the system going, we're going to have some Expanse 101 training, probably late September, and then training for transition for Comet users in October. And that's when the production starts too. And this just tells you all the allocation options, and you can go look at the submit page there. So just to summarize, I think I've gone over, so let me go through quick. It's essentially going to be a huge increase in throughput, more than 2x of Comet. And in terms of benchmarks that we've seen anywhere between 1 to 1.8x improvement on a per core basis. And I do want to say big thanks to Dr. Panda and the MVAPICH team for providing MPI implementations for various SDSC systems over the years, Trestles, Comet, Gordon, and Expanse that's coming up. I also have some of the NSF award information, including one that's with Dr. Panda as the PI. This is the collaborative work we've done on the development of a lot of the MVAPICH components. Thanks.
Yes. So thank you, Maidar. Are there any additional questions?